So in the previous lecture we had seen what functions are and some examples of functions. So in this class we will look at some predefined functions in maths. So we will look at them one by one. So the first type we will see today is identity functions. So identity function is defined as if fx is same as x. So if x is 1, fx is also 1. If x is 2, fx is also 2. X is minus 5, fx is also minus 5. So the value of function corresponding to a given element is the same as the value of element. So we will define it as f from real number to real number, and it's defined by fx equal to x for each x belonging to R. So pictorially we will see how this function looks like. So in the last class we had seen that whenever we want to draw a graph of a function, we first draw a table. So since this function is very simple, we don't need to draw a table. We can directly plot. So this is our x-axis. This is negative x-axis. This is y-axis. And this is negative y-axis. Uh, so on y-axis we will plot fx, the value fx, and on x-axis we will have the value x. So if from this function, if x is 0, fx is same as x. So this should also be 0, 1, 1, 5, 5, minus 5, minus 5, and so on. So for 0, it's 0. It's the origin. If this is 1 and this is 1, then for 1 it's 1. So it will be here. And then 2, 3, 5 is somewhere here. And let's say 5 is somewhere here. So for 5 it will be somewhere around here. For 3 it will be here, because for fx for 3 is 3. For minus 5 is somewhere around here. So when x is minus 5, y is also minus 5. And now we will join these points. So it will be a straight line at an angle of 45 degrees. So this angle is 90 degree. It exactly divides these two lines in the mid. So it's a straight line. That's why because for every point it should be the same value on x-axis and y-axis. for any value. If we take any point on this, not necessarily integers, we can take 3.5, then y will also be 3.5. So that's our identity function. Next we will see constant functions. So here fx was changing. So when x was changing, fx was changing. But for constant functions, no matter what the value of x is, it will always be a constant. So let me first write the definition for this. So this is again from R to R, and it's defined as some constant c. So whatever where c is constant. So c is a constant like 5 or 10 or any constant value. So whatever is the value of x, this is independent of x. So it will always be the same value. So for example, we take an example. So let's our constant is 5, fx equal to 5. This is our constant function. Then if we take x and take y, so x is 10, y is 5, x is 5, y is 5, x is 0, y is 5, x is minus 2, y is 5. Y is always constant. We have written here fx is c. It's constant. So its plot will be like this. So this is 5. This is origin here. One, two, three, 4, 5. So this is for fx equal to 5. Because you see, if 10 is somewhere here, what is y? It will be here. If x is 5, somewhere around here, then also y is 5. If x is 0, then also y is 5. If x is minus 2 here, then also y is 5. So this will be a parallel line passing from 5, the line parallel to x-axis, that is horizontal line. So this is our constant function. So our third kind of function is polynomial functions. So it's defined as some constant plus a1 x plus a2 x square plus an x to the power n. So this so here we have a polynomial function, and its a0 is some constant. These a0, a1, a2, these are all constants, some number. And sorry, this should be in the superscript. And we have different powers of x. So we have x to the power 0 here, so that is 1. We have x square, we have x cube, and so on. So some of these may be missing. So a0, a1, a2, these, if x square term is not there, we will say a2 is 0. So n is some positive number here. So n is, or better say non-negative integer, and a0, a1, a2, these all are real numbers. So for example, we can take fx equal to 2x cube plus x square minus 5. So this function is in this form. Why? Because we have x cube. So here the maximum power of x, that is 3. So here n is 3. So this n is 3, and this an is 2. 2 is what? An, or in this case a3. So a3 is 2, and this a2 is 1 here. So we can write 1 into x square. X is missing, so we will take 0. So a1 is 0, and this a0 is minus 5. So this is in this form where n is some non-negative integer. These powers of x, the powers of x should be integer. So if we have 5 square root of x, then this means 5 x to the power of 1 half, and this power is not an integer. So this will not be a polynomial function. Here all the powers of x should be integer, non-negative integers. So then only we can say it's a polynomial function. Similarly, we have say 2x to the power 3 by 2 plus 5. Then again, this is not a polynomial function. So some example, in the last class we had plotted y equal to x square and y equal to x cube. So these are examples of polynomial functions. Here we have n equal to 3, an or a3 is 1, but all other terms a0, a1, a2, these are 0. Here n is 2 and a0 and a1 are 0 and a2 is 1. So for x square we had seen that the graph was like this, and for x cube we had seen that graph is like this. So in the last class we had plotted these graphs. So this was our polynomial function. So next category of functions is rational functions. So in set theory, in number theory, we had seen rational numbers. So rational numbers were denoted in p by q form, where the denominator q should not be equal to 0. So similarly for rational functions, it should be of the type fx is one function and gx is another function, where both fx and gx, these are polynomial functions these are polynomial functions of x, and gx this gx should not be 0. So in rational numbers also we have to say that p by q, where q is not equal to 0, because if this gx is 0 then this entire function will not be defined. So let this function is px equal to fx divided by gx. So here gx should not be equal to 0, otherwise this function will not be defined. So we can take, in the last class also we had taken one example. We had plotted y equal to 1 by x, where x belong to real numbers excluding 0. So we had plotted this in the last class we had plotted it using table. So this is 1, this is -1, so for 1 it's 1, for -1 it's -1, for 10 it will be 1 by 10, very small number, for 5 1 by 5, and for 0.5 it will be 2, for 0.3 it will be 3. So we had seen that this its plot was something like this. And similarly on the negative side. So for 0 it's not defined, for number just greater than 0 it's plus infinity, for a number just less than 0 it's negative infinity, and here positive infinity. So it's not defined at 0. So this was our plot for 1 by x. So that's why its domain is all real numbers, all the numbers on this real axis, excluding this value 0. So this we had seen in the last class. So here also fx is 1, which is a polynomial function. So 1 is also a polynomial function here. All a1, a2, a3 and so on, these will be 0, and this a0 will be equal to 1. So 1 can also be represented as a polynomial function, and similarly x can be represented as polynomial function. So here both 1 and x are polynomial functions, fx and gx. So this function 1 by x, it's a rational function, and the plot for 1 by x is like this. So the next type of function that we will study today is modulus function. So it's a function defined from R to R, defined as f of x equal to, so it's denoted as these two vertical bars and x, and it's read as modulus of x. So we will read it as modulus of x. Whenever we see this, we will read it as modulus of that number which is included within that. So here x belongs to real number. And we will define it as x when x is greater than equal to 0. So if x is greater than equal to 0, then this is same as our identity function. So identity function was fx is equal to x. So for x greater than 0, that is this part from 0 onwards, it will be same as this. But for negative part, when x is less than 0, then we will say minus x. So if this is 2, then it will be 2, because x is greater than equal to 0. So it will be same as x. If it's 1, then it's 1. If it's 0, then it's 0. If it's minus 2. So if x is less than 0, then we flip the sign. So if it's minus 2, we will write 2. If it's minus 5, we will write plus 5. So this output is always positive. This is always positive. It can never be negative. Because if x is positive, we leave it as it is, and if x is negative, we will change its sign. So make it positive. So its plot would look, for the positive part of x, it will look similar to our identity function. So for positive part, it will be same. This is our y-axis. For any value, if it is 5, so if it's 5, y is also 5. For negative, if x is negative, like it's minus 5, then we change this sign. So minus 5 become plus 5. So y is plus 5. If it's minus 1, then y is plus 1. Now we will join this. So this is the plot for y is equal to modulus of x. Our next function is Signum Functions. So we will define Signum Function as one when x is greater than 0, 0 when x is equal to 0, and minus 1 when x is less than 0. So this is our definition for Signum Functions. So it's defined for all the values of x belonging to real numbers, and whatever value of x we take, either it will be greater than 0, either it will be equal to 0 or less than 0. So it's defined for all values of x. So its domain, we can say domain will be the set of real numbers. So similarly for our previous functions, we can define the domain and range. So here domain is the entire x can take any value, any real number. So domain is here real number. And what is range? Range is only positive real numbers, because y can never be negative. So this was for modulus function. Similarly for other functions, you can see what are domain and range. So for Signum function, domain is the entire real numbers because it's defined for every real number. And what's its range? So whatever is the value of x, it can take any of these values. So either it will be 1, 0 or minus 1. So range is just this set, minus 1, 0 and 1. Now we will plot its graph. So if x is 0, then this is 0. So one point would be here. If x is greater than 0, so for 0 it's here. If x is greater than 0, then it will be 1. So for any point we take here, for 1 it's 1, for 2 it's 2, for 3 it's 3, for 0.5 it's 1, for 1.5 also it's 1, for 3, 4, 5, 6, for everything, every positive number it's 1. But at exactly 0, it should be 0. So this side it's 1, a constant function. But at 0 it's not 1, so we will draw a hollow circle here to denote it's not this 1 at this value, and here we draw a solid dot to denote at 0 it's 0. Similarly for negative, if it's -1, then it's -1. For -2, -1. For any negative number, it will be -1. But not at this 0. So we will draw a hollow circle here and then join this point. So this is our Signum function. And it can take only three values, either -1, +1 or 0. So its range is this. Now we will take one more function for today. So our next category of functions is greatest integer function. So we define greatest integer function as this symbol, this square brackets. So for a modulus function we had straight bars. For greatest integer function we used square braces. So we will denote it as this, and its meaning is, so here again it's defined for all values of x. So its meaning is like this. We will read it as whenever some number is written within square brackets, then it means that the value of the greatest integer less than or equal to x. So it means the value of the greatest integer less than or equal to x. So that's why it's called greatest integer function. So if it's we will take an example. If x is 1.5, so this is our x, this is fx. So if x is 1.5, then we have to find the greatest integer, but it should be less than or equal to x. So what are the integers which are less than or equal to x? So these will be 1 is less than 1.5. We cannot take 2, 3, 4, 5 because these are more than 1.5. So 1, 0, -1, -2, and all other negative integers. So the greatest among these integers is 1. So it should be less than this x, and it should be, so there are many integers less than this x, but we have to pick the greatest, the largest integer among them. So these were the integers less than x, but the largest among them is 1. So its value will be 1. Similarly, if we have 1.6, it will be 1. 1.7, it will be 1. But if we write 2, so the integers should be less than or equal to, it can also be equal to. So for 2, we have integers 2, 3 we cannot take, 3, 4, 5 because these are more than x. So 2 is less than or equal to x, 1 is there, 0 is there, and all negative integers. So the greatest among these is 2. So for 2 it will be 2. So for any integer it will be same as that. And so if it's between 1 and 2, then it will be 1 excluding 2. So if it's 2, so for 1 and 2, 2 is excluded. We denote it using this small braces. and 1 is included in this set. So we will use square brackets for 2 to 3. So for values like 2, 2.1, 2.2, 2.3 all the way up to 2.9999, but excluding 3, it will be 2. If it reaches 3, then it will be 3 and continue till a value less than 4. Similarly, if it's some negative value, if we have minus 1.5, so even for negative integers it will be same as that. So if it's minus 1, it's minus 1, minus 2, minus 2. If it's minus 1.5, then what are the integers less than minus 1.5? So minus 1 is more than minus 1.5, so we will not write minus 1. Similarly 0, 1, 2, 3, these are all more than 1. So the integers less than minus 1.5 are minus 2, minus 3, minus 4, and all other negative integers. So the largest among these is minus 2. So for minus 1.5, the value is minus 2. For minus 1, it will be minus 1. For minus 2.5, it will be minus 3. But for plus 2.5, it will be 2. So this should always be less than or equal to x. So minus 3 is less than minus 2.5 and 2 is less than 2.5. So now we will plot its graph. So for 0, this should be 0. For 0.1, again it's 0. For 0.2, 3, 4, 0.9, here suppose we have 1. And here 2, then 3. This is x-axis. And this is y-axis. So from 0 till this point, just before x, just before 1, it's 0. But at 1, its value is 1. At 1, it's not 0. So here we will draw an hollow circle. So here we had drawn a hollow circle, so it means that at this point its value is not this. So similarly from 0 to just before 1, it's 0, but at 1 it's 1. Similarly from 1 till this point 2, its value is equal to 1, but exactly at 2 it's not 1, it's 2 at exactly 2. So we will draw a solid circle at 2. And similarly from all the values from 2 to just less than 3. So 2.1, 2.2, 2.999, it's equal to 2, but at 3 it's not 2. At 3 it's 3, and so on. Now on negative side, minus 1, minus 2. So if it's 0, then it's 0. If it's 0, then it's 0. If it's 0.1, minus 0.1, then it cannot be 0 because 0 is more than minus 0.1, and this function's value should be less than whatever is x. So if it's minus 0.1 here or minus 0.5, then this should be minus 1. Similarly minus 0.1 till minus 1, it will be minus 1, but at 0 it's not that value. So we'll draw a hollow circle here and a solid circle here, and then this is minus 2, minus 3, So for minus 2.5 it's minus 3, minus 1.5. So for minus 1.5 it will be this minus 2. So at minus 1 it's not minus 2, so we will draw a hollow circle at here, and from here till minus 2 we will draw this minus 2, and for values between this minus 2 and minus 3 it will be equal to minus 3. So we will draw a hollow circle here and then solid here, and then again hollow here and solid here. So this will be the plot for this greatest integer function. So in these were the main types of functions. We have many more functions. We will study trigonometric functions like sine, cosine, inverse, cosine, tan, many other functions when we study trigonometry and other chapters. So till now, these were the main categories of functions. So that's all for this lecture. Thanks for watching.